Morning. Let's get started. So today we're going to do more sorting. So last time we did bitonic sort, and today we will be doing simple sort. And yeah, I think the next homework is there. So it's on bitonic sorting and communication primitives, and you should have everything you need to do the homework now. So yeah. So last time we did bitonic sorting, and bitonic sort is an example of a regular algorithm. And regular algorithm means that it has the same amount of work, or the same amount of data, and also relatedly the same amount of work on every processor. So if you remember, bitonic sorting is like a sorting network, and basically what happened is that in the simplest case, we put one comparator of the sorting network on every processor when n was equal to p, and so every processor in each round there are n over 2 vertical wires in each column, and each pair of processors has to do one swap potentially if the min and the max were flipped depending on the direction of the wire. And if we generalize to the case where n is greater than p, then each processor takes the place of multiple data points, but pretty much we distribute the data evenly across the p processors as evenly as possible. If n does not perfectly divide p, maybe some might have a little extra, but it's pretty much evenly distributed, and the work is also evenly distributed. In each round, you have to do this merge split, which is proportional to n over p. But everybody has to do that, so the work is pretty much uniform. And on the other side, we have irregular algorithms, which are, for example, like simple sort, or for example, like quick sort, where the work the data in the work are variable across the processors. So if you know about quick sort, which we will talk a little bit about shortly, you do this like randomized partitioning, and you try to cut evenly as possible, but you may, it's random, so you may get some imbalance, and that's where the irregularity comes from. So this is just the visualization. The work is these bars. So if you have 4 processors, in regular algorithms, the work is pretty much even, and in irregular algorithms, the work is it's non-uniform. Some processors may have more than others, and the total time is bounded by the longest running processor. So the program or the algorithm is not considered finished until the last one finishes. And so the lower bound on the time is the longest one. The main trick that we're going to use today in simple sort is something that happens a lot in distributed memory computing. So in practice, we want to minimize the communication cost because we have these constants for measuring communication cost like mu and tau. And mu and tau are both, so the constant in front of computation is, that's normalized to 1. So that's like unit cost. And both mu, which is the cost to transfer per byte or per element, and tau, which is the startup cost to starting the communication, are much higher than 1. And so ideally, we would like to minimize communication as much as possible. And especially, so we want to minimize the communication cost relative to some ideal time. And the ideal time for some parallel algorithm is always the serial time, t sub 1 over p. Because if you have p processors, each of them can do, in some sense, like p units of work in one step. And so the maximum or the minimum time that it could possibly take if you have t sub 1 units of work is t sub 1 over p. And that is like the work law that we learned in work span analysis, but it's also true in distributed memory. The minimum time, if you have this serial time, the maximum, or another way to say it is the maximum speed up that you can get is p, because if you have p processors. And so since computation time is cheap relative to communication time, one thing that we can try to do is do a little bit of extra computation and minimize, in order to minimize the amount of communication that needs to happen. So to recap from last time, we did bitonic sorting. Bitonic sorting is this kind of sorting network where basically there's 2 main steps. The first one is you form 2 bitonic sequences. The first half is going up, the second half is going down. And then you perform a bitonic merge on the entire thing to make the final sorted sequence. And the computation time, so this is the time to sort on one processor. If we have any n log n sorting algorithm, and the input size on each processor is n over p, then it is going to take n over p log n over p time to sort on one processor. And then the second part is the part, so this part is just like in some sense like the base case where you sort on one processor, and then this one is the computation time to do the combination in the bitonic merges. So there are log squared columns in the sorting network, and each of them does each of the merge split does n over p computation time, because what is happening in each one of the comparators when n is greater than p, you have two processors that are paired up with each other. Each of them has order n over p data, and they need to merge their data in a sorted way and then cut it so that the smaller half is on one and the bigger half is on the other, depending on the direction of the vertical arrow. And for communication time, so there are logs, this is the way they analyze it, there are log squared column or log squared p columns in the sorting network, and each of them takes tau plus mu n over p communication time, because each pairing of processors needs to communicate. Oh yeah, go ahead. What do you mean the same computation? Like they may not be either. Like you're saying if you have a regular algorithm for a problem and an irregular algorithm for the problem? Hmm? Both, ideally. Modulo, like if it doesn't evenly divide, maybe some have a little bit extra, but as even as possible. But you may have regular and irregular algorithms for the same problem that don't have the same runtime. Like, for example, bitonic sorting is a regular algorithm for the problem, for the sorting problem, but like quicksort is an irregular algorithm for the same problem, but quicksort is n log n, whereas bitonic sorting is n log squared. So, yeah, being irregular doesn't really tell you anything about the individual runtime of the algorithm, just about the distribution of the work. Good question. So going back to this communication time, the way that we analyze the communication time, there are log squared p columns in the sorting network. Each column, in each column, the processors are paired up with each other, and they have to do this exchange of n over p elements. So that's where this tau plus mu n over p comes from. And so like this is just expanded out, but it's like log squared p times quantity tau plus mu n over p. And so for bitonic sorting, this is good. This is just the time to sort on one processor. And it doesn't seem like we can hope to do that much better than this, because like we at least have to sort the individual problems on each processor. And however, there's this extra n over p times log squared p term, which is not ideal, because if p is large, then this log squared p may become larger than log n over p. And also for the communication time, there's also this extra factor of log squared p. So yeah, so there's this log squared p because there are log squared p columns in the sorting network, but ideally we would like to bring this down. People remember bitonic sorting? Is it clear how you get these runtime bounds? Yes, go ahead. Yeah. That is just a good question. So this assumes that the thing is already block distributed. So if every processor already somehow has the n over p data on it, and that's just the time to sort the individual, like the n over p data that you have. So can we hope to do better? Ideally, we would like to do better because we have lower bounds for sorting in the comparison model, and for sequential algorithms, that's n log n. And here we have something like if p is equal to n, this is a factor of log squared. So ideally, we would like to bring it down. One way to see how far we can go is we can try to prove lower bounds on communication and computation in this parallel model. So if we remember, the sorting lower bound is n log n, and we want to bound the computation and communication lower bounds. For computation, we only have np, because that's the amount of just like operations that you need to do. And communication has this extra tau and mu factor, because because you may need to do exchange, which takes startup cost tau and individual cost mu. So maybe we could start with the easier one. The serial sorting lower bound is n log n. And so for the computation time, can you think of a lower bound for in terms of n and p? If we set p to 1, we want computation time. We're going to start with a lower bound on computation time. Yeah. So if you have n data points and p processors, I'm asking for a lower bound on the computation time for sorting. Um, yeah. You can do something a tiny bit stronger, but pretty much yes. So if we go back to this, the ideal parallel algorithm time, if you have p processors, and serial time is t sub 1 p. If t sub 1 is n log n, which is the best that we could do on one processor, then the lower bound is t sub 1 over p. So that's slightly less than, like, the whole n log n, the whole thing divided by p, is less than n over p times log n over p. Wait. No. Yes. It's more than that, a little bit, actually. Yes, because like then the front thing is n over p, and then the inner thing is log n. So we actually have to do a tiny bit more than the time to sort on one processor. But like, does that make sense? Because like n log n divided by p is just n over p log n, and so this is slightly less than that. So we're gonna have to do a tiny bit more than that, but it's close. Good. Is that clear to everyone? How you get lower bounds on parallel time? So if you have a lower bound for sequential algorithms, the lower bound for p processors is just that divided by p. And computation time or communication time is a little bit harder. So we can talk about that individually. So the first thing is just what I said. For sequential sorting, we have an n log n lower bound. So the computation lower bound is just n log n divided by p. For communication, it's a bit harder. And here, this is just sort of a very loose bound, which is that if you have n over p processor or n over p elements in each processor, in the worst case, all the n over p elements are going to have to move somewhere else, because like you're trying to sort it globally across all the processors, and maybe, for example, like all the max elements were in the front. It's possible. And so in the worst case, all n over p elements are going to have to move somewhere else, which is going to cost you mu n over p to move them. And even in the average case, if n over p, so you have n over p elements per process, and maybe in the very like evenly distributed case, n over p, so you have p processors, and let's say n over p squared belong to each other processor. So that's just n over p times 1 over p. Then you're still going to have to move n over p elements. And so by this sort of loose argument, the lower bound on communication, we can say, is mu n over p. So this is so in the average case, like in the worst case, like on one processor, everything is going to have to go somewhere else. This is kind of like an average case saying, let's say for each processor, you divide it up by p, and each section that you divided up is going to have to go to one of the. So like if you evenly distribute your elements onto all p processors, you're still going to have to ship basically n over p elements, because only like n over p squared elements will still belong to you. questions on this part? So we have lower bounds for computation, which is n log n, the whole thing divided by p, and communication, which is mu n over p. Actually, there should be like a tau plus mu n over p, but in the limit, this thing will be bigger. So that's why it's omega. Okay. So yeah, this is just repeating these lower bounds, n log n over p, and mu times n over p for communication. And this is just the same bounds repeated again for bitonic sort. So how far are we from these lower bounds? Well, we are not reaching them, especially in communication. The lower bound is mu n over p, and what we have in communication is log squared times that. So ideally, we would like to get rid of this log squared factor. And also, in communication, if n is equal to p, then this is also higher than the lower bound because this is like n over p log squared, whereas the lower bound is log. So ideally, we would like to do better, and that is why we're going to do a different sorting algorithm. But the different sorting algorithm uses bitonic sort as a subroutine, so it's still interesting to learn bitonic sort, and also it's still worth it to learn bitonic sort because that's regular, and you can build sorting networks really fast. Right. So can we do better? So in an ideal case, if we had some magic sorting algorithm, everybody would get equal blocks from everyone else. So one issue with this lower bound, well, you can't do better than this lower bound because even if everybody got equal blocks from everyone else, we would have to still ship basically n over p elements. But it would be evenly distributed if you could equalize the blocks from everyone. And also, ideally, the blocks would be in order. So like on each processor, the block that has to go to processor 1 and 2 and so on are ideally in order on the processor. Yeah. So one way to try to do this is to do parallel quicksort. So it doesn't totally solve this issue because, as we know, quicksort, it might have imbalance. And so not everybody may get equal blocks. But quicksort is sort of like an intermediate step on the way to try to understand sample sort, which is going to try to achieve this case. So in quicksort, how we're going to analyze it in distributed memory. In the beginning, we have p processors. Each of them has something like n over p data. And the first step is we pick the pivot. In each recursive step, we pick a pivot, and we have to broadcast the pivot to everyone, which is going to take log p times tau plus mu if we have p processors. So this is just the broadcast runtime that we had when we were doing communication primitives. And once everyone has the pivot, we partition the elements locally on the processor. So like everybody now has the pivot, and we need to move the elements around the pivot. That's going to take time order n over p because everybody has n over p elements, and you can do those all in parallel. That's just independent work on each processor. And then finally, we have to rearrange the partitions. So all the stuff left of the pivot has to go in the first half of the processors, and all the stuff to the right of the pivot has to go in the second half of the processors. And that, on average, is going to take tau plus mu n over p. Because everybody has n over p elements, and ideally, you have to ship about half of them if you pick your pivot perfectly correctly. And then in the recursive case, then you just split the processors in half. So you have p, then you split them like p over 2, and then you just repeat the process. So these are the two halves, and so on until the base case where p equals to 1. And then in p equals to 1, then you just locally sort the elements that you have. Questions so far? Is it clear how we get these bounds for communication and computation? So tau and mu only come up when you have to move elements between processors. So that's why it came up in this broadcast case and this rearranging case, because here you have to move the pivot, and here you have to move the actual data. But this part doesn't have any tau and mu because once everybody has the pivot, you can just rearrange your elements locally on your own processor. So in the in expectation, assuming that you pick the pivot totally correctly, the height of the recursion is log p. The computation time is, so this first part, or the second part is local sorting, n over p, log n over p. We just had that also in bitonic sort. You just sort on one processor. And to do the exchange, sorry, to do the partitioning, each round takes n over p, and you have to do it log p rounds because the height of the recursion is log p. So that's where this n over p log p comes from. And this is order n log n over p. You can choose a different, so you should choose a different pivot within the subproblems. Like just like when you do sequential quicksort, you change the pivot when you recurse. Because the thing that like in the ideal case, you pick like the global median in the top one, and the global median may not be the median for the subproblems. So that is the computation time, which is better. So this reaches the lower bound in expectation and log n over p. The communication time is, so this part, mu n over p log p, comes from, in each round, you have to exchange, you have to do this partition rearranging. So that's where this comes from, mu n over p, and you do it in log p rounds. And then this tau log squared p comes from this broadcast. So in each recursive step, you have to do something like log p broadcast time, and you have to do it log times. So that it's not bad in expectation. However, like in the worst case, it could be much worse, because if you pick the pivot wrong, then the whole thing could be totally imbalanced. Like you might have just one element in one of the subproblems and n minus one in the other subproblem. Mm-hmm. This one? Yeah, this one is just in the base case, when p equals to 1, then you run any n log n sorting algorithm that you have. The problem size when you reach the base case in expectation is n over p. So that's just you plug n over p for the input size. So it's n over p log n over p. Good. Okay. So just to recap, these are the lower bounds. So the computation time reaches the lower bound in expectation. The communication time is higher. There's still this extra factor of log p, even in expectation, because like the lower bound was mu n over p, and this is mu n over p times log p. You can get rid of this if you use the same random number generator on every processor. So like the pivot doesn't have to be something that's actually in the dataset. So if every processor has the same random number generator and you just run the same generator, then you can get rid of the broadcast. But you can't get rid of this data exchange, because once you pick the pivot, you still have to put the smaller stuff in the left and the bigger stuff in the right. Yeah, and this expectation case is ideally if you magically pick the global median every time, then you can reach this this expectation bound, but it's a randomized thing. So we are good on the computation lower bound, but the communication lower bound is still a log factor off. So ideally, we would like to lower this into the lower bound for communication. Questions so far? So yeah, so like kind of coming from quicksort, the motivation for sample sort, or like the high level idea behind sample sort, is rather than picking one pivot, you choose something like p pivots, where p is the number of processors that you have. And ideally, if you magically chose your p pivots correctly, you would distribute your data not into two parts, but into p evenly sized parts, where each of those gets evenly shipped to the different processors. So we're going to try. The first try is that we choose p. It's basically like quicksort, except rather than one pivot, you choose p minus one pivots, because that will give you p partitions of your data on each processor. Instead of guessing one, you guess p minus one. So the first step is that you sort the elements locally, which is taking this amount of time, n over p log n over p, because the input size is n over p on each process. Then step 2 is to pick p minus 1 global random splitters. And that is going to take p log p time. Yes. And then after that, then you do this local partitioning again. The local partitioning is also n over p, because it takes the same amount of time to like, it doesn't matter how many splitters you have to partition your local elements. It's still taking n over p time. You just need to put them into buckets according to the p minus 1 splitters. Then finally, we do this all-to-all communication, where so each process now has p partitions on it based on these splitters. Everybody has the same splitters. And then we do this exchange, and each process has some data destined for processor 1 and processor 2 and so on. And so you just ship that data from each process onto processor 1, processor 2, all the way down. And so now after this all-to-all, everything that is in the first partition is on processor 1. Everything that is on the second partition is on processor 2, and so on up until processor P. And so the data is like, it's sorted like across the bucket boundaries. So like everything less than the first pivot is in processor 1, and everything between the first and the second pivot is in processor 2, and so on. So this is not like a recursive thing. This is just one round. And if we could locally merge those sequences, then we would be done. Because like all the data is within boundaries, like size boundaries. And if you just merge them into a totally sorted list on each process, then the whole thing would be globally sorted. Yeah. In the ideal case, all the local arrays are always evenly split. All of them are magically evenly split into p parts, where all the p parts are evenly sized if you chose the pivots somehow magically correctly. However, like in the worst case, the imbalance could be up to similar to n, because like if you choose the pivots wrong, like in this case, many more elements are going into this last one than in here. Questions? People clear on like the general flow of this algorithm? Like it's different from quicksort in that there's only one round. Like this is not a recursive thing. Once you pick p pivots and you do the exchange and sort, like the whole thing is done. So in an ideal case for simple sort, you would choose p minus 1 good splitters, where it evenly splits the data on each process evenly to go to all the other processes. And the definition of good splitter is that each processor should receive something like a constant factor of n over p elements, where c is like similar, where c is something similar to 1. So everybody should receive approximately n over p elements in this many-to-many step. It might not be exactly n over p, but it should be something like theta n over p. And also finding these good splitters should not be too expensive relative to the total cost of the algorithm, because if we did spend more time finding the splitters, then we would just be blowing away the computation lower bound anyway. And the high-level goal is to bring the communication time similar to this lower bound. And this is hopeful because like the only communication step is so far is like this one, which is the many-to-many exchange, this does reach the this is the lower bound when n grows larger. Like this whole thing will be dominated by mu n over p for large n. And also, ideally, this would like to be deterministic, so we don't run into randomized worst cases. And finally, yeah, this merge step, how can you efficiently merge p sequences? This has nothing really to do with communication time, but it's just something, it's just like a trick, an algorithm trick that you can learn. So if you have two lists, it's easy to merge them. Like you always take the min from, like you take the smaller min and you attach it into the thing that you're merging into. If you have p things that you're trying to merge, it takes log p time to take the min from each from the p list, because like you can compare them basically in a binary tree. The height of the binary tree is log p. So if you have n over p elements that you're trying to merge, it will take n over p, or sorry, you have n over p elements total, and there are p lists. It takes n over p log p, n over p times log p. It's just computation time. It's assuming that all the lists are already on one processor, which we can assume because this step was after the many-to-many exchange. So that's just how we got this runtime, n over p log p. So going back to this, in an ideal simple sort, we would find good splitters, where good splitters means that we, as close to evenly as possible, divide the data to go to each processor. Once we do this partitioning, we merge the L. So every processor after this exchange has p lists that it needs to merge. So it takes log p per element to do this tournament merge. There are approximately n over p elements, and that's where this runtime comes from. And the crux of the algorithm is how do you find good splitters to try to do this even distribution? And the way that they do it in simple sort is by oversampling. So the goal is to pick p good splitters, but for oversampling, we pick more than p and choose p good ones from the ones that we chose. And you choose something like p squared, something similar to p squared. So to choose these good ones, this oversampling scheme is like this. You pick from each sorted array. So the first step is to sort locally. The second step is to choose in each local array, you choose p evenly spaced elements in each local array. So the p elements per processor, or p minus 1 elements per processor, might be different across the different processors. And you can do that easily because it's locally sorted on each process, so you can choose like p evenly spaced elements in the array. So every process now has p minus 1 splitters, and that evenly divides the elements on that process. Now we combine them and sort them all using Pythonic sort. So we have p processes, and each one has p minus 1 splitters, so they're going to be p times p minus 1 total local splitters. And we can sort those. We just put them all in one process, or we don't even need to put them all in one process. We just Pythonic sort the entire thing using the algorithm that we had from last time. And then at the end, each process will end up with, so each process started with p elements. Each process will end up with p splitters as well. Then from those, you pick p minus 1 global splitters. And the way that you do that is you have something like p squared splitters across the entire, across all the processors. Then you just choose p minus 1 evenly spaced ones from those after you sorted. And it's also easy because you have an array similar to size in p squared, and you just evenly choose like every p or so. And then finally, everybody needs all the global splitters, so you just all gather them. So maybe one thing that we have been doing is like we did these communication primitives, but we kind of just did them in the abstract, and I promised that you build distributed memory algorithms off of these communication primitives. So you can see like this one is using all gather, or like the exchange is like many to many. So these are just basic things that you use to build the algorithms. Yeah. So this is just notation. You get these you get p-1 global splitters from p times quantity p-1 local splitters. This notation is just like from processor 0, it has 1 up to p-1 splitters. Questions? Okay, so this is just an example of how this is going to go. So let's say we have 3 processors, P1, P0, P1, P2, and they all have just 7 elements on them. And so the first step is to locally sort the elements on each processor, and then pick p-1 local pivots or splitters on each process. So for P0, for example, we just sorted all these blue elements, and we pick just 2 elements evenly spaced, because there are 3 processes, so p-1 is 2. And this is evenly dividing P0, or evenly dividing the elements on P0. And we do the same in P1 and P2. So P1, we sort the yellow elements, and we pick evenly spaced elements here. And same on P2. So now we have 6 local splitters, because that's 3 times 2, because it's like P times p-1. And then we combine them, and we sort them. So there's something like p² local splitters that we're trying to combine. And we choose p-1 evenly spaced splitters from those. So we have 6, and it doesn't perfectly divide, but it's as even as possible. If one of the partitions is going to have one more. So we sorted these. Each of these has equal contribution from the different processors, but the global splitters might not have even contribution from the different processors, and that's also fine. So here we chose 8 and 17. And then somehow every process needs to get these numbers 8 and 17. So that's just through all gather. And finally, use those to partition all the elements. So every process gets 8 and 17, and then it splits its own array into things that are less than 8, things that are between 8 and 17, and things that are greater than 17. Or things that are at least 17. I think it's non-inclusive on the right side. And that local partitioning just takes time n over p. Actually, you don't actually have to do any partitioning exchange because the whole thing is already sorted. So you just have to do like a binary search into the entire array to tell you where the partitions end. And then finally, now you have the different processes, or now you have, so for example, like here, the pivot is 8. So 1, 2, 7 are going to stay on processor 0. 13 and 14 are going to go to processor 1. And 17, 18, and 22 are going to go to processor 2. And in P1, so partition is 8. So 3 and 6 are going to stay, or 3 and 6 are going to go to P0. 9, 10, 15 are going to stay on P1. And 20, 21, 24 are going to go to P2. And something similar in P2 as well. And then, yeah, so you do this partition. Yes. Go ahead.
Is it possible to handle the case where all array elements will not be distinct?
It's possible to handle the case. I think you may have to attach an additional kind of index on it because, like, in the case where all elements are not distinct, like ideally you would like them all to be evenly distributed across different processors. But if you naively run this, I think they may all try to end up on the same processor because if the partition is like, yeah, like if all the global splitters are this, like in the worst case, all the elements are the same, and then all the local splitters and then all the global splitters would be the same. And so the partition, it has to be somehow clearly defined, like where if all the elements are, like if it's non-inclusive, then it's not clear without a secondary index where they should go, because then the partition is empty. Does that make sense? Yeah. So you could do a secondary index, sort of like a stable sorting type of secondary index. Yeah. I think for simplicity, we're assuming that they're all different. It's easier to see that way. But yeah, it's slightly more complicated. Yes. Other questions? So we choose these global splitters, and then we partition the elements, and and then we sort them through the tournament merge that we were just talking about. So in the end, everything that is on, so before the tournament merge, everything that is on P0 is between -infinity and 8 non-inclusive on the right side. Everything that is on P1 is between 8 inclusive and 17 non-inclusive. And everything on P2 is at least 17. And so like the buckets are sorted on the different processes. The final step is to merge them into locally sorted lists. So the last step in this is that you want to show that the load distribution is something close to even. And the whole reasoning for doing this oversampling is that we wanted to get rid of the worst case imbalance where you choose the pivots and maybe almost all the data goes onto one processor. And so we want to show in this theorem that each processor gets at most 2n over p elements, something like theta n over p. And the proof is like this. So the number of local splitters in the elements received by each processor is p-1, because the way that we choose the global splitters, there are at most p-1 local splitters between each global splitter by construction. Like we had something like p squared local splitters, we choose p-1 of them, and so there are approximately p between each of them. They may come from any process, but that is how many there are. And so for this notation, if S sub I is the number of local splitters that came from some processor P sub I, and if you sum up over all of I for S sub I, then you get p-1, because each processor contributed p-1 splitters. The maximum number of elements that comes from, so to each process, we're thinking this as like from the point of view of one processor receiving elements. So we're trying to bound how many elements we will receive from everyone else. The maximum number of elements that comes from some processor P sub I is S sub I plus 1, which is the number of local splitters that came from the process, plus 1 times n over p squared, because the local splitters divided the n over p elements on each process into p pieces. So each individual piece that was split is n over p squared. And so the total number of elements that are received by the processor, you just sum up over 0 up to p-1, something like over p, and then this quantity, s sub 1 plus 1 quantity times n over p squared. And if you do out the summation, this is just n over, it's like p times n over p, or p times n over p squared, which is just n over p. And this, we said the summation of this thing is bounded above by p-1. So this thing is also, this whole thing is bounded above by like n over p. And so if you add them up, this thing is at most n over, it's less than n over p, but it's at most n over p, and this thing is exactly n over p. And so the whole thing is bounded above by 2n over p. Okay. So yeah, so that's the reasoning behind sample sort about. So basically what happened is that we oversampled, but we didn't oversample arbitrarily. We chose, we combined these local pivots into some global pivots, and then we tried to prove some bounds on how evenly spaced or how much data will come to each processor given these global pivots. So by simpling these good splitters, we chose these local splitters, we combined them using Bytonic sort, and then we chose p minus 1 evenly spaced out of that array, and then we all gathered them. The complexity, yeah, and this is the, recall the cost of Bytonic sort, which is if you have n greater than p, then the complexity is this thing, local sort time plus n over p log squared p. And communication time is tau plus mu n over p times log squared p. So the complexity of selecting the global splitters, well, it's just the cost to do the Bytonic sort for p squared elements, because there's some local cost, like local computation cost, but that's basically free once you have already sorted the local elements, and the only cost is coming to combine the elements. So you have p squared elements that we need to Bytonic sort. The computation time is p log squared p. That's just plugging in p here. And the communication time, yeah, so this is just, just plugging in p squared for n in these bounds. So the computation time is p log squared p. The communication time is mu plus, or tau plus mu over p times log squared. And then you have to pay the altogether cost, which is just, this is plugging p into m for the altogether cost. So the whole goal of simple sort is to bring the communication time closer to the lower bound. And in the very beginning, I said the way that we're going to do that is we pay a little bit of computation time to try to reduce the overall asymptotic communication time. And we do pay like a little bit more communication time here, but this communication time is proportional to p rather than n. And so it will go away in the big O because the lower bound on the communication is relative to n. Okay. So finally, to put it all together, so choosing these good splitters is these green ones, which is what we just had on the previous slide. This is the cost to do the Bytonic sort plus the altogether, pretty much, but that's dominated by the Bytonic sort. The time to, yeah, this blue one here is the time to do the local sort in the computation time. This purple one is the time to locally merge p sequences, so n over p times log p. And in the communication time, this orange one is the many-to-many cost. So that's the, after we have chosen the splitters and after we have done the Bytonic sort, that's just the time to do the exchange of the partition. And yeah, so if you simplify it, if we look at the communication time, that is tau plus, or tau p plus mu n over p times mu times this thing. And so the lower bound, we just repeated it there, is ideally like this thing. And the whole thing is dominated by this term if n is greater than p squared log p, because this is just p log squared p. So this whole thing would become bigger than, or n over p becomes bigger than this when n is greater than p squared log p. Or sorry, p squared log squared p. Yeah, and so that brings it to the communication lower bound for large n. And also the computation time is, for large n, this term is bigger. N grows, but like p doesn't usually grow. P is kind of like fixed in your machine. Yeah. So that's the end of simple sort. So simple sort is used more in practice than Bytonic sort probably, but like I said, it uses Bytonic sort as the subroutine because you have to sort the pivots. And also, like from an implementation perspective, this is harder to implement than Bytonic sort. Like Bytonic sort is pretty easy to implement because you just need to build this logical sorting network between the processes. And if you remember from last time, like the pseudocode was like 5 lines. But here, simple sort, like you have to do, it's a bit complicated, like you have to choose the pivots, and you have to exchange them, and then you have to exchange the data, and the data is not necessarily exactly uniform to exchange. So it's slightly more complicated to implement. Questions? If there are no questions, I have a little bit of time, so I guess I can move on. Okay. 1 second. Oh, I see. Maybe. Okay, cool. Yeah, so for the next topic, we will be doing embeddings. Yeah. So embeddings, so we're moving on from sorting. We're done with sorting. And yeah, so embeddings is not on the next homework. The next homework is currently out and it is on communication primitives and sorting, but embeddings will be in the next homework and in the following exam. So I'm gonna do it. Yeah, so embeddings are basically trying to map different topologies onto each other. Because if you remember, we were talking about hypercubic permutations before, and hypercubic permutations are permutations like of exchange between processors, where the processors that are communicating are differing by only 1 bit. So yeah, it could be any of the bits, like, but in a strict hypercubic permutation, it has to be the same bit that is flipped between all of them. So like you could flip the lowest bit, for example, and then that would be the two close by pairs communicating with each other. Or if you flip the top bit, that would be like the two farthest away pairs communicating with each other. If you had ordered the processors left to right. There's another relaxed version of hypercubic permutation, which is that the bits don't have to be the same in the index. So in regular hypercubic permutation, you have to fix which index bit of the bit you flip, but in relaxed ones, any of them can be flipped. But that can still be supported by a hypercube. So hypercube is just this thing where for every bit index, you are connected to things that differ in 1 bit away from you. So that clearly supports hypercubic permutations, because in hypercubic permutations, you only communicate with things that are differing in 1 bit away. So for 1 bit, this is a line. For 2 bits, this is a square. 0, 0 is connected to 0, 1, 1, 0. But it's not connected to 1, 1 directly, because 1, 1 differs in 2 bits from 0, 0. And then for 3 bits, 0, 0, 0 is connected to 0, 0, 1, 0, 1, 0, and 1, 0, 0. So that's for d dimensions, every node has d neighbors, because for d, like if your bit length is d, then there are only at most d positions that you can differ in 1 bit by. So that means the neighbors is bounded by the number, like the bit length. So embeddings they're basically a function that maps source topologies to target topologies and vice versa. So if you have a source topology, like any kind of source, well, in a moment we'll talk about different kinds of topologies, but topologies are just ways that the nodes in the network are connected. So like hypercube is one type of topology, and that just defines, like, if you had 8 processors, these are the processors that can directly communicate with each other via links. And yeah, so this is a hypercube topology, which is one kind of topology. And the reason that we have so many different kinds of topology is, like, for a while ago, I was talking about how in a very ideal case, like all all the processors would be connected to all the other processors directly. But the problem with that is that that would require p-squared links, which is infeasible in practice because p can be quite large. And so we have to build networks. The ideal network has something similar to p-links, because like that would be minimal cost. So for embeddings, you have some algorithm that is designed for the source network. And you actually have a target network, which is this is so this is the system that you actually have. You would like to design algorithms for a source network, maybe because it's logically easier to design it for those things. And you want to run the algorithm logically on the source network, but you want it to achieve primitive runtimes of the target network. So the most concrete example that we'll have of this is like when we do matrix algorithms, it is easiest to think of the matrix algorithms in terms of like a grid or a 3D grid or whatever it is, because you think of the matrix as logically divided up on the grid. And that's the easiest way to think about the communication. But it turns out that if you actually have a grid, the runtimes for basic primitives can be not as good as you want them to be. And so like we want to achieve hypercube primitive runtimes, but logically we want to think of the algorithms as running on the grid. That will hopefully become more clear later when we do matrix algorithms. Basically what happens is that, yeah, so some algorithms are more easily expressed in some types of topologies, like grid, but you actually want some nice theoretical runtimes that come from other, maybe harder to think about topologies like hypercube. And so the reason for embeddings is that you can map between these two types of topologies using some function on the nodes. So these are just two graphs. You have some function on the nodes, which will give you also some function on the edges. And you just simulate the algorithm on the source topology on the target topology using this function translation. And yeah, the source and target are graphs. So the nodes are the processors, and the edges are the direct links between the processors. And yeah, and so we are mostly going to be in the case where this target network can support relaxed hypercubic permutations, because when we were doing communication primitives, we had nice bounds on communication primitives in the hypercube. Questions? Yeah, and the high-level way that all these embeddings go is that we have a graph, some source graph. The nodes in the graph are numbered by some bit strings, and we define some function to map the bit strings of the source nodes to some bit strings of the target nodes. Mhm.
What we want is, say we have one node in, and then we want to figure out which node we want.
Yes. Yes, basically, yeah. So we run the algorithm in A. So for example, like let's say A is a grid and B is a hypercube. Like logically, we would like the two neighbors in the grid to communicate, but those may not actually be neighbors in the hypercube. But it's like it's hard to think about the communication in the hypercube, and so that's why we just map the nodes between the two topologies. Mhm. Ideally, yes. There may be some cases where it's not, but we will go. Yeah, good question. In a moment, we will go through like different metrics for embeddings. Yeah. Other question? Okay. So yeah. So the ideal case for an embedding is, to answer your question, we'll go through it in a second. It's called a mapping, which is like a one-to-one function between both the nodes and the edges. But there are different performance metrics for embedding because it may not necessarily be directly one-to-one. So for the edges, there are two. So you have a source graph, which is just some set of vertices and some set of edges. You're trying to embed it into a target graph, G prime, which is just B prime and E prime. And like the set V may be equal to the set V, or it might not. And the set E might be equal to E prime, or it might not. And so there are two metrics. The first one is congestion, which is the maximum number of edges from E that are mapped onto a single edge in E prime. And that just tells us like if two distinct edges from E are mapped into the same edge from E prime, then uh, like when you actually try to, so you simulate the algorithm on the source topology, you actually run it on the target topology, which is what you actually have. And so when you actually run it on the target, you would get congestion on that link because two processors are trying to send along it. And the second one is dilation, which is the maximum number of edges in E prime that any edge in E is mapped to. So you have one edge in E, and it may not, like the two connections in E, or sorry, the two vertices that edge connected in E may not be directly connected in the target graph. And so that's where dilation comes from. Like you may have to do multiple hops for what was in the source topology one hop. Yeah, and the communication would slow down by a factor of congestion times dilation, because congestion, like you cannot send multiple things along a link at one time. You can only send one thing in this model. And so like if two things are trying to send, then that serializes the communication. And the dilation would also slow it down because rather than sending along one link, now you have to send along two. So when you do this function translation, some edge in your original graph G might be mapped to a path in G prime, where path is, I mean, one edge is also a path, but like what I mean here is that maybe it gets mapped to multiple edges, multiple contiguous edges in G prime, like this. So like if you have this blue one and this red one in G, it might get mapped like this. Like this blue one becomes two edges in G prime, and this red one becomes these two edges in G prime. And so the edges in G, you have multiple, so here the dilation is 2 because one edge becomes 2, and also the congestion is 2 because two edges are going along this link. Are people good on like graph structure? Yes. So those are the basics for edges. And for nodes, there's another two metrics. One is called load, and load is the number of nodes in V that are going to map into a single node in V prime. So it does not have to be like a one-to-one function. And expansion is the number of nodes in V prime to that in V. So like the number of nodes in V prime could be more than those in V, or less. The computation would slow down by a factor of load, because if two nodes are mapped onto one node, then like that one node in the target topology has to do the work of the two. And if you have expansion of more than one, that's a waste of resources, because like you can't, it's not necessarily true that you could parallelize the work of one processor onto two processors. It's possible, but like it's not guaranteed. And so, yeah, ideally you would like to have a one-to-one mapping on the nodes. So a mapping is a special case of an embedding where the load, the congestion, and the dilation are all equal to 1. So ideally, we would like to generate mappings between topologies because then there's no, so congestion and dilation are both 1, so the communication is unaffected, and the load is 1, so the computation is also unaffected. And this is the high-level goal. So I think the main confusing part of this is sometimes it's hard to keep straight like which one is the source and which one is the target and which direction we're trying to go. But if you can remember that, then I think that's most of the difficult part. And for our purposes, the target is something that can support a relaxed hypercubic permutations. So for most cases, a hypercube is sufficient. So if you have an embedding that is a mapping, you only need to specify the node because the edge mapping just falls out of the node mapping if all the properties are satisfied, like all the previous performance properties that I said are satisfied. The parallel runtime on the target topology is the same as the runtime on the source topology, because if the load and the dilation and the expansion are all one, then both the communication time and the computation time are the same as in the source topology. It doesn't say that the parallel runtime would be good, it just says that it would be preserved. And similarly for the efficiency, if you're mapping from the source, if you have a mapping from the source to the target, the efficiency is the same because the parallel runtime is the same. That's also not to say that the thing is efficient. Like if your algorithm was inefficient on the source, it will be inefficient on the target as well. It just says that the efficiency is preserved. And yeah, it's possible that there can be a better algorithm. So like if you have an algorithm that is good on the source topology, it's possible that if you had directly designed an algorithm for the target, you could reach a better runtime or a better efficiency. This is just to say that you preserve the efficiency when doing the function mapping. Yeah. But that's not an issue if it's already optimal. So if we have lower bounds for some problem and your algorithm achieves the lower bound on the source, it will also achieve the lower bound on the target. Okay. Questions so far? So the simplest type of topology is an array or a ring. And this is just, these nodes are the different processors, and like the array is the most simplest one. They're just connected in a line like this. And these are the processes that can directly communicate with each other. And if, for example, like if this one wanted to communicate with this one, they'd have to first send to this one, and then that one would forward the message on. And the generalization of an array is it's a ring, and a ring is just like it has the wraparound link at the end. So 0, if this is like 0, 1, 2, 3, 4, here in array 0 and 4 are not connected, but in a ring 0 and 4 are connected. Yeah. So first one is that we want to embed a ring into a hypercube. And it also applies to an array because an array is just a subset of a ring. And the way we're going to do this is by translating the bit encodings of the original ring indices into hypercube indices. So the ring indices are just laid out in order, 0, 1, 2, 3, up to 7, just left to right. And so these are just this is how you write them in binary. Or sorry, this is how you write the binary of the target mapping. And so this is like, so notice that these are different from the original. So these are the source, and this is the target. And these are different. The source and the target are different indices. In most cases, 0 and 1 are the same, but here like 3 and 2 are flipped. And 4 and 5 were here, but 5 and 4 go there in the target. Almost out of time. So next time we will show actually how to do this mapping. But the reason that you can't just directly map the source ranks into the target ranks is because the original ring topology doesn't support hypercubic runtimes in the original thing. So like it doesn't. So not the things that are connected in the ring are not necessarily differing in 1 bit. Like for example, 3 and 4 differ in more than 1 bit in the original binary representation. So that's why we need to do this, because in this mapping, now everything, all the neighbors differ by only 1 bit. Yeah, and we will continue that next time. Oh yeah, please go ahead.
In this diagram, 0 and 2 factors.
Yes. 0 and 3. So 0 is like 0, 0, and 3 is 1, 1.
No, I mean, 0 and 2 in the
I see. Like 0 and so the binary representation for 3 is 1, 1. So it could, they were not directly connected in the hypercube or in the ring. But 0 and 1 are connected in both the hypercube and the ring because they differ by only 1 bit. But we cannot exactly simulate the entire hypercube because like for even a bit string of 3, we would need 3 neighbors per node to simulate the perfect hypercube, but we cannot get more edges into the ring. So yeah, but we're trying to satisfy this property that all the neighbors in the target mapping differ by only 1 bit. So thank you. We'll continue next time.